Good afternoon, everyone. Today we're going to look at a tan function graphed, and we're going to get the function that represents this curve exactly. So, first things first, let's look at the period, which is the distance between two consecutive asymptotes. I'll remind you, these vertical dashed lines are vertical asymptotes. And those are precisely when our function is undefined, which is to say when we're dividing by zero because of the tan function, because of tan being sine over cos. I'll remind you that tan of theta is sine theta over cos theta. And so whenever cos theta takes on the value of zero, which it does from time to time, we get an undefined function which produces a vertical asymptote at those specific values of theta, or x in this case. So let's first off start by noting that the distance between two consecutive asymptotes is from negative pi to positive pi, which would mean a period of 2 pi. Okay? Now our regular tan function has a period of 1 pi, right? Negative pi over 2 to pi over 2 typically. And so now, since our period is twice as large, we know that the period of a tan function is always pi times the horizontal stretch, and so this is clearly stretched out by a factor of 2, which means that our horizontal stretch is 2, and that also tells us that when we're writing our equation in transformational form, our b value is the reciprocal of our horizontal stretch, meaning a b value of 1/2. Okay? Now, our starting point, which is kind of the point in the middle, strangely to say for a tan function, but I hope you guys know what I mean. Our starting point is this one that I'm referring to. Starting point over here. This point is at 0, 1, whereas typically for a tan function that has not undergone any transformations, that starting point is smack dab at the origin. Now it's shifted up by 1 vertically, and so that tells us that we have a vertical translation of 1. And so we know that already we'll have +1 at the end. This is a tan function. And so we have tan of, our b value is 1/2. So we know it's going to be tan of 1/2. And now, do we have any horizontal translation? That is, any translation in the x direction. And again, if we look at our starting point at 0, 1, which is the middle of this kind of curving region, we can see that it's not shifted right or left. There was no horizontal translation to our starting point. And so that means that we're not going to have anything inside the brackets of x minus or plus something else. We're just going to have tan of 1/2 x. We can put brackets around 1/2 x. They are redundant, but I know that's often how these functions look, and so feel free to add them in if it makes you happy. And the last part of it is going to be, typically, we go over by pi over 4, and we go up by 1 to get to our next key point, right? Usually. Now, we know we don't go over by pi over 4 this time, because we already found that we underwent a horizontal stretch of 2. That means everything horizontally is being stretched apart by a factor of 2 times as wide. And so instead of going over by pi over 4, we're going to go over by twice as much, right? So we're going to go over by 2 times pi over 4, which of course is pi over 2. That's why from our starting point to our next key point, we go over and back by pi over 2, right? That's our value that we see here. And now we have to note how much we're going to go up by, because typically with the parent tan function where no transformations are at play, we go over by pi over 4 and only up by 1. But here we notice that we go from 1 all the way to here pi over 2 and 3. And so we know we went up by 2. And so that means that we went up by 1 times our vertical stretch, and that has to be equal to 2, and so obviously that implies that our vertical stretch is 2, right? We went up by 2 instead of 1, and so we get a vertical stretch of 2, and so we can tack that in front of the tan. This does go from low to high, which is symbolic of a positive tan function, and so there's no Rx to note in negative up front here. And so we've taken care of our horizontal stretch, we've taken care of our vertical translation. We said there was no horizontal translation, so we can make a note that the horizontal translation is non-existent. And finally, we have our vertical stretch of 2. We know that there is no reflection in the x-axis, so this is a positive tan function. And so we've looked at everything that we could possibly look at, and so we conclude that this tan function is represented by y is equal to 2 tan of 1/2 x plus 1. I hope this helps. I hope you start seeing the connections between the graphs and the functions themselves. Again, a reminder of how tan is fundamentally written and where the vertical asymptotes come from. Namely, they come from where cos of whatever we're looking at takes on the value of 0. In this case, this would be the asymptotes would be when cos of this stuff, so cos of 1/2 x is equal to 0. Okay, we can even look at when that would be. So looking at that a bit further, that means that 1/2 x is equal to the inverse cos of 0, which means that 1/2 x is equal to, when do we get a cos value of 0? Cos is the x coordinate, so that'll be at pi over 2, and 3 pi over 2, and 5 over 2. So at pi over 2, plus or minus pi radians around our unit circle. So pi over 2, we get our cosine of 0. Oopsies. 3 pi over 2, 5 pi over 2, 7 pi over 2. Now, right? Any multiple of pi radians, we get another cosine value of 0. And so that means we can rotate around the unit circle in multiples of pi radians. So plus or minus pi k, where k can be any element in the set of integers. And now, I know it's a little, this is perhaps something new to you guys, but if 1/2 x is equal to all this, then we're going to multiply both sides by 2, right? And so we'll have that our vertical asymptotes, which again arise when the cosine of whatever we're looking at in the function takes on the value of 0, and then that happens when the x values are pi, which times 2 is just pi, and then plus or minus the 2 multiplies both parts, right? So 2 times pi k is now plus 2 pi k, where k can be any element of the set of integers. And so we do see that happening. Pi over 2 is our first, pi, excuse me, pi here is our first vertical asymptote, right? So we get one vertical asymptote at pi. Then if we subtract 2 pi, which is 1 full period's worth, subtracting 2 pi from pi takes us to negative pi, where we again see a vertical asymptote taking shape. And we go in the other direction. If we added 2 pi, that would take us to around over here, let's say to 3 pi, and we would get another vertical asymptote at this point. Again, noting that the plus or minus 2 pi k, that's not random, that's not by coincidence, that is precisely, where did we write it out? That is precisely, we didn't really write it out, yeah, where our period comes into play, right? This is our period, and the period is what dictates how often we're going to see the vertical asymptotes, because again, the period is precisely the distance between each consecutive vertical asymptote. Okay, and I hope you guys start to see the connections between all these things, how to get the cosine values of 0, where the vertical asymptotes arise, how tan being equal to 0 is when sine is equal to 0, because 0 over anything is of course 0, as long as it's not 0 over 0, which is a particular example we'll get into a bit later. But in any case, I hope this helps. Thanks for watching. If you guys have any comments, questions, suggestions, please leave a note below, and take care.